Hello. In this short video, we are going to discuss exponential functions, exponential growth and exponential decay, and I will discuss the idea of a relative growth rate, and this will help us characterize the special property that exponential functions have, and we will solve a differential equation to see that, in fact, exponential functions are the only ones with that particular property. So suppose I have an exponential function, this function f of x here. A and b are some unknown constants. Those are just fixed real numbers. Whatever values they have, this is an exponential function. And as I noted a little bit further down here, if that b value is positive, that's what makes the function exponential growth. I would see that kind of growth curve. And conversely, if b is negative, that's what would cause exponential decay, and I would see a decay curve, a graph kind of like that. So by growth rate, I mean derivative. The growth rate of the function is its rate of change, how rapidly it's changing, the derivative, and in this case, by just applying the chain rule one time, that's where that times b is coming from, then here's the derivative that I would get. And notice that, in fact, that's exactly b times the original function itself. The derivative of e to the x is e to the x itself. And when I have e to the b times x like this, the chain rule pops out that extra multiplying factor of b. So in this case, the growth rate, the derivative of the function, is a multiple of itself, a multiple of the function. It's proportional to itself. So when I say down here relative growth rate, I mean as a proportion compared to the original function. And so I can actually see that for exponential functions like this, because its derivative is a multiple of itself, then that relative growth rate, this proportion of the derivative divided by the function itself, I get exactly b, and it's important to note that that is constant. So as we can see here, exponential functions, be they growth or decay functions, exponential functions have a constant relative growth rate. That's what I meant by this term up here. So by growth rate, I mean the derivative. By relative growth rate, I mean as a proportion compared to the original function f itself. And by constant, I mean that it turns out to be a specific number. Let's explore some graphs to see what I mean by that. You can pause the video and visit this Desmos URL down at the bottom. I will open up the Desmos graph on my tablet here. I've put together a graph where I have an exponential function, f of x, here, and you can use the slider bars to change the constants a and b, or you can just go in and type specific numbers for them. I'll leave it at 1 and 1 right now, so we are looking at the red curve, which is just e to the x itself, because a and b are both 1. Down here, you can see I've created a box that says f prime of x sub 1 divided by f of x sub 1. So that's a relative growth rate. That has the derivative of a function divided by the function itself. And in this case, they're both evaluated at a particular point, which is what the x sub 1 means. Now you can change that point by moving the slider bar here for x1, or you could just click and grab the point itself and move it back and forth as you see fit. So I'll put it right here on the y-intercept just to have something specific to look at. Oops, I missed by a little bit. It's harder to do than it looks. So you can see that that's a constant of 1. Desmos shows you the evaluation of that. And as I move x1 left and right, notice that that value does not change. That ratio, that proportion, is always 1. And in fact, it shouldn't surprise us based on what we saw on the slide, because that's the value of b. What if I go up and I change the function? Let's change b. Notice that as I increase it, it makes the exponential growth more rapid. As I decrease it, I make it exponential growth but more slow. And then as I make b negative, it actually turns into exponential decay. So let's make a really steep exponential growth curve, like making b 2. Hey, look at that. That relative growth rate, that proportion, is now 2, and it turns out it doesn't matter where I move my point. It's always 2. In fact, as I change a, the multiple in front of the function up here, that also changes the steepness of the curve. It's like multiplying, it's scaling up the function if I'm multiplying by a number bigger than 1, or it's scaling down the function if I multiply by a number less than 1, or on top of both those things, it's flipping it across the x-axis if I multiply by a negative number. But no matter what a is, notice that that's not changing that relative growth rate. It's always the value of b. For any value of a, and for any point on the curve, it's always that value of b. So now we've seen that exponential functions, be they growth or decay, have a constant relative growth rate. And we might wonder, are there other functions that do that? Or is there something special about the exponential functions that have this property? And as it turns out, exponential functions are the only ones that have that property. Well, except for the boring old constant function f of x equals 0, which is its graph is a flat horizontal line, its derivative is 0 everywhere, its function value is 0 everywhere, so it's kind of a boring way, a trivial way of satisfying this differential equation that asks for the derivative of the function to be a multiple of itself, because the multiple of 0 is always 0 no matter what. So what we're going to show here is solving a separable differential equation to demonstrate that only exponential functions come out of this process. So up here, when I say f prime of x, let's think of that as the output y, its derivative with respect to x. This is another notation we have for writing derivatives. And that's equal to a constant b times y, the function f of x. So when I say over here f, I'm going to write that as y. And when I see f prime, the derivative, I'm going to write that as dy dx. So based on what we discussed in a previous video, specifically the one about Newton's law of cooling and separable differential equations, I can start to solve this by dividing both sides by y and multiplying through on both sides by the dx. I've now separated the two main variables, y and x. Remember that b is a constant. So now that we've separated the two variables, I can start to make some progress on solving this equation to obtain a function y equals f of x by integrating both sides. On the right side, I'm going to get b times x. The antiderivative of a constant b is b times x. And then there's always that plus c that's going to pop out when I have an antiderivative like that. Meanwhile, on the left, the antiderivative is natural log of y. Then I can start to solve this by raising e, the base, to the exponent of both sides. On the left side, e to the natural log of something returns that something. And on the right side, I have e to the bx plus c, which I could also simplify by applying a property of exponents and writing it as a product of two exponential terms with the same base. And then I could even just say, you know what, c is just an arbitrary, a random constant, so e to the c is also just a random constant number. So I'm just going to write this as y equals, let's just call e to the c a, just some arbitrary constant. So that allows me to write y equals that constant a times e to the bx. And look, that's exactly the exponential form of the function that we expected to get. This shows that the only solution to this differential equation, which asks for a function whose derivative is a constant multiple of the function itself, the only solutions to that differential equation are exponential functions like this. Now, just as a short little aside, you may have quibbled about my working over here where I said e to the natural log of the absolute value of y is just y itself, and you might say, hey, Professor Brendan, what about the absolute value bars? What happened there? Well, as it turns out, those are just based on the sign of a. If a was a positive number, I didn't really need those absolute value bars all along anyway. And if a was a negative number, I could have just written a negative instead. So really, those aren't anything to worry about. This is still the form of the function that is the solution to this differential equation. I know that explanation will not satisfy perfectly all the technical details, but for the context of my class, that's enough that we need to get into for now.